So just a word about the schedule. So Chris Stock is our last speaker for today. And then we have lunch, and at 1 o'clock we have a panel discussion on careers. Everybody wants one, right? Okay, so prepare your questions. How much money do you want to make? How many hours a week do you want to work? Less than you. Anyways, prepare your questions. We have, I'll introduce the panel. We have a few people joining us in addition to whoever else is here. It's very informal, and we'll discuss. It's very informal, and we'll discuss any questions you want to raise or issues or anything you want to know. Okay. And then tomorrow there's a panel on academic integrity. As I mentioned, we have some guests for that as well. All right, so as we move on, Chris Stock is at the University of Edinburgh. I've known Chris for quite a long time. We were grad students together. He's wrong. And thank you for coming east to visit us and to give a talk here. So please go ahead.
Okay. Yeah, thanks very much, JP, for the kind introduction. Yeah, so as JP mentioned, I'm Canadian, so that's why I don't have a Scottish accent. So just in case people are wondering. Oh, sorry, can I ask a question? Do you have a laser pointer?
Oh.
Yeah, sorry.
Is this not?
Oh, no, sorry.
This one?
Yeah.
There's another one there. This one.
Ah, cool. Okay, thanks. Sorry.
What?
That's perfect.
Like that.
Oh, okay.
Answer slides too.
Okay, sorry. Give me a second. Thank you. Oh, brilliant. Okay, yeah, thanks. Thanks again, JP. All right. So in today's talk, actually, I wanted to give kind of an introduction, first of all, to neutron scattering and try to, well, I know you're going to see the NCNR tomorrow, so hopefully I'll make the case to you why neutrons are so useful. But then also talk about magnetic excitation in neutrons, with using neutrons, why that's useful and what sort of information that gives. But also, as you can tell from the title, I really want to make the case for spin-orbit coupling in magnetic excitations and why that kind of changes the picture and what new types of excitations we can give. So let's see if I can get this to work. Okay, yeah, so this is kind of the outline of this talk. So first of all, actually, I kind of inserted a slide yesterday just talking about neutron scattering and why that's important. Then I want to talk about magnetic excitations, in particular the issue of spin-orbit coupling and the collective excitations we get out of that, and kind of the theory that we use to actually extract information from neutron scattering. And then I want to look at some examples, actually. Oh, sorry. Some examples. In particular, I want to focus on calcium ruthenate and cobalt oxide, and you'll see why those examples are interesting in the talk. And then finish up with some work we did on MGB204 and a compound called NBCP, which is a very good refrigerator. Hopefully I'll make the case for that. But anyways, the big goal here is I want to actually really make the case for why single ion physics is important for neutron scattering and also magnetic excitations. And also maybe I'll point out why I think it's being kind of overlooked and a little bit loved. Okay, but first on to neutron scattering. I know that tomorrow,
You click on the screen again.
you're on screen. Okay, thank you. Sorry. Yeah, okay, that's perfect. Thanks. Okay, I know tomorrow that you're going to have a tour of the NCNR, but I wanted to kind of just spend a few minutes making the case for neutron scattering. With any experimental technique, you basically want to always match the resolution of the technique that you're using to kind of what you're measuring. And kind of a crude example of that is if you think about, I don't know why I'm picking this example, but a pothole or a crater on the I-270, you wouldn't go look at that and characterize it with an STM or an SEM. Well, you could, but it's not going to be particularly useful. You'd want a meter stick or a measuring tape because the resolution of those two instruments are a lot better matched to kind of the distances that you're after and trying to characterize. Now, in condensed matter physics, if we think about the energy scales and the length scales that we're interested in, so let's first of all think about length scales. So we're interested in atomic properties. So the typical unit cell length, if I want to think about strontium titanate, barium titanate, any of those compounds, you're talking a unit cell length of something like 4 to 5 angstroms. I know with some of these photovoltaic materials recently, that number is creeping up to 7 or 8 angstroms. But the point is the kind of order of magnitude that we're interested in is sort of angstroms. That's the length scale that we're interested in. In terms of energy scales in condensed matter, we're interested in kind of KBT on the order of room temperature, right? And if you take 293 or 300 Kelvin and convert that to millivolts, you get something like 25 millivolts, give or take a bit, but it's on the order of tens of millivolts. So these are the energy scale we're interested in. It's about 10 millivolt-ish, and we're interested in length scales of about an angstrom. Now, if you go into synchrotron X-rays, for example, and you take your length scale of about 1 angstrom and you figure out what the energy of the photon is you need to have that wavelength, you come up with a massive energy scale of 12 kiloelectron volts. Now, remember, we're interested in 10 millivolts. Also, kind of just as a sideline, photons, which are X-rays, have no magnetic moment, and they interact with material via the electromagnetic force. So they really kind of interact with electrons. Now, with neutrons, on the other hand, like you'll see at the NCNR, first of all, neutrons are massive. They come with a spin, so they have a magnetic moment, and therefore they interact with the magnetic moment of a material by a potential that looks something like this, m being the magnetic moment in your sample, and sigma being the spin of the neutron. Okay, now, if we take a wavelength of a neutron, because it's massive now, and convert that into energy, we take our favorite 1 angstrom, we come up with a much smaller energy scale, about 80 millivolts. The point is, that's tens of millivolts, and that's very well matched to the type of excitations we want to measure in condensed matter physics. So neutrons are actually neat, because if you can get the right wavelength, you get automatically the right energy scale that is kind of useful to your problem. And furthermore, just like at the NCNR, neutrons are produced through an equilibrium process, at least at reactor sources, and the KBT that defines the Boltzmann distribution is about room temperature, which is about 25 millivolts. So the neutrons actually get produced at copious amounts with the right wavelength and also the right energy scale for the problem that we're interested in. And importantly, for this talk at least, they have a magnetic moment too. So we're sensitive to first order in interactions through this potential to the magnetism of the material. Okay, now a lot of people get annoyed with me with this because they think I'm trash talking synchrotrons. So that's not the point here. Synchrotrons come with the big bonus that you have flux. I did have a slide, but we don't have time, showing that kind of the flux, the number of neutrons you get out of the source, like the NCNR, is kind of well matched to kind of a low-level lab X-ray source. So that's a really important thing with synchrotron X-rays, is you really got the flux that we don't have with neutrons. But with neutrons, that's why it's very important to kind of match the resolution and the instrument with the problem that you're actually trying to study. And that's actually a whole nother talk and hopefully you'll hear about some of the instruments that are available at the NCNR tomorrow. Okay, now onto the kind of the main point of this talk. I pointed out that neutrons are sensitive to the magnetic moment of a material. And if you want to characterize the magnetic interactions in a material, one way to actually do it is to actually measure normal modes. Now, that shouldn't be a big surprise, because if you think about a spring attached to a big mass like a wall or something, with a particular spring constant, that's going to have a characteristic frequency that goes as square root of k over m. So if you can measure that characteristic frequency, you can understand the interactions. And that's the issue with neutrons too. If you can measure the normal modes, the collective excitations that occur in the spin dynamics, for example, you can understand the underlying interactions. And kind of a nice model for that is if you think about a magnetic system, which is made up of a series of vector spins with a fixed length, and you want to study collective excitations from that, you want to look at excitations that look something like this, where there's kind of a weak transverse movement of the moments as you go over a particular wavelength. And this is a normal mode of the system. And the equation that kind of dictates that, a lot like F equals to kx, if you want to set up a differential equation for that, for a spring, is really this equation here. And this is the Landau-Lifshitz equation. And this just tells you that for on a given moment, you have a molecular field, which is this h here, that's defined by the neighboring spins, and that the dynamics of that spin is just defined by this precession. So you can think of this as a precession along a particular magnetic moment direction, or molecular field direction, h. And that molecular field, which is really important, it's going to keep coming back in the next kind of half an hour or so, is determined by the interactions. So if you have an exchange interaction that couples these spins, that ties them together, the molecular field that acts on one of these is simply given by this formula here. It's the exchange interaction times the magnetic moment of the neighboring spins. Now, you can solve this equation here to first order, and what I mean by that using perturbation is that you assume that the molecular field is constant for all the spins, and then you can set up a series of first order equations and basically crank through the linear algebra, and you're done. And if you end up with, if you do this for a ferromagnetic chain, you end up with a dispersion relation, which is the energy as a function of Q. Remember, Q is 2 pi over lambda. So you can think of down here, you're looking at very long wavelength excitations. And as you increase Q, you're looking at progressively shorter and shorter. But this relation here, which you can measure from neutrons just by fixing Q, scanning the energy transfer, there's a number of ways to do that with neutrons, and seeing where you hit a peak, which is where you cross this dispersion. It's actually determined by this relation here, and you see you can immediately extract the exchange constant. But the key thing here is that the dynamics really are fixed by kind of this molecular field, which corresponds to the interactions times the spin. Now, this can get annoying, I have to say, if you do it by hand. But the good news is that we have a lot of software now, and in particular, one of the nicest packages is a software called SpinW, and there's a paper that discusses about this. And it will do all the heavy lifting for you. There's a lot of nice tutorials out there that tell you how you can set up the magnetic structure, the nuclear structure, and come out with these interactions that define how these spins are coupled to that. And just to kind of give a nice example of that, this is rubidium manganese fluoride. It's a two-dimensional magnet made up of manganese, and manganese here is in the high spin 5/2 state. So this is a very classical magnet. And this is actually a picture here of taken on a chopper instrument where you've crossed the dispersion relation, if I could just back up here, and you're taking a momentum slice at a fixed energy. So if you think about, for example, sitting at 1 here and doing a cut, you'll get a cone that you can actually, where am I? Yeah, here, that you can actually see with the neutron spectrum. So you can get the velocity of that dispersion relation I was talking about and get the exchange coupling constants. And you can also get an idea of local anisotropy that was talked about in the previous talk through this gap right here. So neutrons actually provide a direct measure of the exchange interaction, and as well as this anisotropy. Now, this is a very simple classical model, right? You see, I've set up a series of spins, and I've looked at collective excitations over long length scales. Now, let's think about other types of magnetic excitations we can get. Let me say I don't have a nice array, for example, a chain of spins that are coupled with this nice J they go on forever. Let's say I give you a system that looks like this. This is a dimer with, let's just say, spin a half, so I can do the arithmetic in my head. You have one spin antiferromagnetically attached to another spin, and that's it. And this is the case in, for example, copper nitrate. This was a paper back in 2000. And this is in some ways kind of a trivial example of a spin liquid state, because in this case, you have one spin that's attached to another, and that's it. It doesn't care about any long-range interactions. It doesn't care about what the next dimer is doing. Yet, the excitations of this are sharp. Now, if you want to think about what kind of excitations exist from this, well, you can actually do the quantum mechanics in your head. So if these are two spin-a-half objects, we have this thing called the addition theorem that tells you, okay, if I want to think about the total angular momentum of the system, that I'm going to end up basically with two possible values, right? I'm going to have the case when I subtract a half and a half, so I get 0. And then there's going to be another state where they're added, and that's got a J total of 1. You can get that, so you can solve this immediately if you kind of know the addition theorem of angular momentum. It's a bit of a trick, but it turns out to be really useful. Now, with an angular momentum of 1 thing you have to keep in mind is that state has 3 possible values, right? You can have a z-axis projection of 1, 0, or -1. That's what angular momentum tells us. So this is a triplet state, and down here it's J of 0. You can only have one possible z-axis projection there, and so this is a singlet state, and that's what you find here. But this is totally different. Linear spin wave theory does not help you to get that. And indeed, people actually measured the excitation spectrum from this, and this is the data right here. They used actually some rules to come up with the model. But you can see here that you have actually a gap that defines the energies between the singlet and the triplet. And because these triplets are actually coupled spatially, it does give you this modulation Q, which you don't quite get here. I'll show you how you can count for that. But there are different types of excitations that standard semi-classical theory that I talked about, they don't really help you with. Now, just kind of seeing what these dimers can do for you. This is an interesting case of thallium copper chloride. This is a system made up of these dimers that at 0 field is basically a spin liquid. You just have each spin coupled to one nearest neighbor. That's it. The system's in its ground state. It's fine. But these dimers don't care about what the neighboring dimer is doing. So there's no long-range magnetic orders attached to this system. But what this experiment here did back in, I guess this is 2008, is they applied pressure. And that had the effect of taking those triplet excitations, taking them to E equals to 0. And what they found is they got an antiferromagnetic state. But the excitations were kind of strange. What they found was they found these nice transverse modes I was telling you about, where you have a fixed spin, that's just now kind of deviating from its direction. That's given by the Landau-Lifshitz equation. But there was one more mode here that corresponded to amplitude fluctuations, modulations of that spin direction. So that's something you can't actually easily get out of that linear spin wave theory. Now, what's interesting here is that this mode plays a key factor. You see, when it softens, you get a nice phase transition. Now, how can we actually get this longitudinal or amplitude mode? Let's just kind of go with this thread here for a minute. So if we want to get this guy to turn on, we need an expression that looks like this. We want the first derivative of Sz with respect to time to not equal to 0. And quantum mechanics tells us is that means we need this observable, Sz, not to commute with the Hamiltonian. And how do we do that? Well, actually a nice place to start is to introduce that interaction right there. If I can get this character playing a role in the Hamiltonian, then I can start getting these types of new longitudinal Sz fluctuations that don't really exist at first order in semi-classical theory. Now, okay, I'm from the University of Edinburgh, so I have to put this up for advertising purposes. All right, so I'm trying to play politics here. But anyways, amplitude modes actually, it's just not an interesting thing in magnetism that comes about because I'm playing with commutators with the Hamiltonian. They constantly appear all the time. For example, if you want to think about your standard Mexican hat energy potential, there's kind of two energy scales that come out of that. First of all, there's this one that goes around the bottom of the hat. You've probably seen this before. That doesn't cost any energy. That's just a Goldstone mode that doesn't cost any energy to excite. And then you get this guy here. That is the amplitude mode that corresponds to fluctuations of the order parameter. And this one's more interesting, right? Because it actually tells you how the bottom of this Mexican hat behaves. And if you start looking at other theories that have nothing, well, that aren't obviously related to magnetism, like in superconductivity, you see this mode appears, and in particular in superconductivity, this amplitude mode is important for the Meissner state. And of course, people have probably heard about this. There was a big deal about the Higgs particle. There is a relation with the Higgs particle, apparently. There's this issue of gauge invariance, so to be honest, I'm not 100% sure of the link, but people make it. But anyways, the issue with the amplitude mode, I think, is kind of nice. But also experimentally, there's actually a nice link with the issues that came out in particle physics. It turns out this SZ mode that I was talking about tends to be higher in energy than the transverse modes, so it tends to decay. It turns out it's quite hard to measure, and that turns out to be the case in condensed matter too. But it is important for characterizing new phase transitions and this potential here. And interestingly, with magnetism, if we can get spin-orbit coupling to play a role and be a relevant energy scale, then basically we're in business. Now, okay, I want to spend a few minutes talking, I know this slide looks awful, but let me explain here. I want to talk a little bit about spin-orbit coupling and when it's relevant and when it isn't in terms of magnetism. Now, I think spin-orbit coupling you can motivate from relativity. It's considered to be a relativistic correction to the Hamiltonian. I think you can also get a long way to that point just thinking about the problem classically. If you think about an electron, okay, I know this is a naive model, but it actually tends to work. If you think about an electron going around a nucleus, if you put yourself in the frame of reference of this electron, you have a different problem. You've got a Coulomb field, so you're seeing at this electron, you're seeing the proton whiz around you. So now you've got a charged particle in an electronic field that's moving. And that's going to produce a magnetic field thanks to the Lorentz force. And if you plug in, okay, notice I swapped the velocity and electric field here to kill off the minus sign. If you do the math here, what you find is that you end up with something that looks like angular momentum. R cross P is L. And you have this factor of Z out here and an R to the cube in the bottom. If you do some gymnastics with quantum mechanics, you can find that that thing actually brings another factor of Z to the cubed into the numerator. And if you go back to that potential I was talking about that goes as mu dot S when I was discussing neutrons, if you put that in, what you find out is that you get something that looks a lot like spin-orbit coupling. Now, this is incredibly naive, and there's some corrections, but I think it's a nice argument because it gets you basically to this point. But another key thing is, because of this, what you find is that this stuff that sits out front of S dot L, which is the spin-orbit coupling, grows as the atomic number to the fourth power. And if you go off and read Landau and Lifshitz, which sometimes can or cannot be a good idea, but I won't talk about that. What they find actually, they start doing further corrections, and they find that this thing actually grows as Z squared, the atomic number to the square. That's fine. The point I want to make here is that the spin-orbit coupling scales with the atomic number to some big power, and that has consequences. So if you plug this in to your typical Hamiltonian where you've got electrostatics, kinetics, and so on, plus spin orbit, what this means is that you have kind of two big regimes of the periodic table. You've got up here where Z is small, so spin orbit coupling is kind of a weak effect. And then you have way down here where spin orbit coupling is the biggest deal. It's the biggest part of the Hamiltonian. And what that means is that if you start doing approximations, is that down here, actually the good quantum numbers, the observables that commute with the Hamiltonian, are actually the total angular momentum squared and its corresponding value Jz. So it's not LSM, whatever. Down here, it's the total J, which is L plus S, and its corresponding Z-axis projection. But when you're up here, for example, you gotta worry about all these characters here. So I wanna just quickly talk about these two different cases here. I wanna start down here, just because we have less observables and quantum numbers to worry about. So if we go way down to the bottom of the periodic table, where spin orbit coupling is big, it's the biggest thing out there, so I have to consider the total angular momentum. Let's take a case, for example, of cerium 3+, where it has a total angular momentum of 5 halves. And in this case, okay, so you start out, thanks to spin orbit coupling, we're considering total J, we have 5 halves. So that corresponds to 6 possible eigenstates, right? So I got plus or minus 5 halves, plus or minus 3 halves, plus or minus a half. And so I will end up here, if I start doing stuff, with a series of Kramer's doublets. It turns out that because it's something divided by 2 or half or something, like 5 halves or 3 halves, not 4/2, which is an integer, there's this other thing called Kramer's theorem that tells you that you have to have doublets in the excitation spectrum unless you got a time reversal breaking field, like a molecular field, like a magnetic field. So, okay, so we start out with our 6 5 halves angular momentum states. We then put that in the crystal electric field, and kind of a cute way of writing that, you could go off and do the Coulomb business, but this will get you there too. This is just equivalent operators called Stevens operators. It doesn't matter. You get the same answer either way. But what you find is that if you put this in the electrostatic field, you end up with 3 doublets here. So you see there's 6. It's always good to kind of count and make sure you haven't lost anybody. Now the single ion physics here, and what I mean by that is the lone cerium sitting in an electric field, not talking to anybody else. So that's the case of not taking a cerium coupled to anybody. It's just a cerium site sitting in the crystalline electric field. That's been studied a lot, actually, for this particular compound, which is cerium, rhodium, or cobalt, indium 5. And they found, actually, surprisingly, that the energy between these doublets is kind of low. It's about 6 millivolts, 6, 7 millivolts, which is about 60 Kelvin. It's not a huge energy scale, actually, between the ground state and the next excited states. Now, to do this, if you look back, think back to the semi-classical theory, it doesn't really work, right? Because here, we're actually changing various levels. We're not doing a semi-classical weak perturbation of a single spin state. So we actually need a new theory. Now, I just want to explain these 2 slides. Okay, this is when usually people start walking out of this talk, but let me explain here a little bit. With neutrons, and I don't have time to explain this, so you can kind of take my word for it at the moment, that the cross-section actually is proportional to the susceptibility. It's the imaginary part of the susceptibility. So it has a nice link with what you would measure with the septometer. Mathematically, a nice way to cast this problem is in terms of Green's functions. And the added value of going to Green's functions is that you can actually solve for it just by looking at the commutator with the Hamiltonian. So the nice thing here is that if you give me the Hamiltonian, I can then calculate what the neutron response is. And our neutron response is going to look, our Hamiltonian is going to look something like this. It's going to have the single ion part, which I've called the crystal field. So that's the electrostatic part. So that's the term I was talking about previously. Plus an interaction. So some exchange constant between 2 neighboring spins here. Now, At this point, you're probably saying, okay, but way back on the first or second slide, I made a big deal about the molecular field, this field put by two neighboring ordered spins on a particular site. That plays a big deal. Okay, you can fix this actually by adding and subtracting that molecular field, and then break this Hamiltonian into two parts where you have an interacting term and a single ion term. So that's kind of the key thing here. So with a little bit of work with the Hamiltonian, I can break it up into a single ion, which is important. That defines these Kramer's doublets or the eigenstates I'm starting off with. And I have an interaction term between that. And if I can then go off and calculate the commutator, then I got the neutron response, basically. Okay, this is the last horrible slide. But the way that actually works out in terms of neutrons is this thing called the random phase approximation. And that's the exact same approximation you make at the beginning with the semi-classical approximation. What you say is that at each site you have a molecular field, just like that H, that's uniform. That doesn't change as a function of site. So that's just basically first order perturbation theory. And what you do is if you calculate the susceptibility at the end of the day, you end up with a small g, which is just built from the single ion Hamiltonian, and you have the exchange constant. So the added value of actually going through all this gymnastics with the Green's functions and breaking the Hamiltonian up is that at the end of the day, if I understand the single ion response that gives me these eigenstates, then, and I understand what this interaction is, then basically I can work back to first order what the Green's function is, and hence the neutron response. This has a nice connection with the semi-classical linear spin wave theory that I was talking about. If you do this whole analysis there, basically the Landau-Lifshitz equation, this precession, corresponds to a transition between these two ground states. So if you think about a spin 5/2 in a molecular field, that's going to split because of the Zeeman effect. And then you're going to have a ground state, which is this z-axis of -5/2. And the spin excitations just correspond to this dipole allowed transition down here. And actually, this tends to work extremely well. I just want to quickly show you some results. This is the case of the cerium rhodium indium 5, where we had these 3 sets of doublets in the single ion response. If we put that in a molecular field, okay, some people have done this, but they've tried to map this onto a semi-classical spin wave theory. But the neat thing about this RPA thing is once you know the single ion Hamiltonian, which is given by calculations, you're basically done, actually. And this is kind of the RPA calculation right here, just using the single ion states. And the neat thing is that it gives you the low energy Goldstone mode that's found experimentally. We've seen it right here. And also, they've measured it at Oak Ridge. But the added value with the single ion response is it gives you this gap mode with no extra gymnastics. That comes about purely from single ion physics. And the neat thing is that it has the right polarization, which is polarized along the z-axis. And that all comes about, this anisotropy, all comes about from the single ion response. Once you understand the single ion response, plug it into the RPA theory, then it just works really well. Okay, that was the case of way down here at the periodic table. The main thing I want to actually leave you with is what happens up here. So this is now when we're at the top of the periodic table, and spin-orbit coupling, remember it scales as z to some power. Landau-Lifshitz tells me it's z squared. So up here, I can't make the approximation that spin-orbit coupling is the biggest energy scale in the Hamiltonian. I have to actually be a little bit more careful. And so as a result, life up here becomes a little bit more complicated because I got to think about the orbital angular momentum and also spin. Now, how do we actually deal with that in 3D transition metal ions? Well, I think this was talked about before this morning, so I don't need to talk about this too much, is that if you put 5D orbitals into an octahedral field, this appears to be the favorite electrostatic configuration in condensed matter physics anyways. This is octahedral environment. it splits the 5d orbitals into a low energy triplet and an excited state doublet. Okay, so that's great. We've got the orbital angular momentum sorted out. Okay, now we got to put in spins. So let's just take the case of vanadium 3+, where there's 2d electrons, because you'll see why this is a little easier to deal with. So if I want to start populating these 5d orbitals with 2d electrons, I have to follow this thing called Pauli's principle, right? That says I have to kind of partially fill each orbital first and then start pairing them up. Okay, so let's do that. So I can do that. I can start over here. I can put 1 in each of the TG. But you might say, okay, I could have done that. I could have done that. Or I could have done that. And that's right. For this case, there's 3 possibilities. And this problem actually maps exactly to an effective angular momentum of 1 in this case. And 1 comes about, you can kind of think of it naively, even though I'll talk about this in a second, that there's 3 possible states here. L of 1 has a z-axis projection of 1, 0, -1. So it's a triplet. We talked about that with the dimer case. So we can maybe map this thing onto an L equals 1 state. That turns out, in the case of an octahedral field, it works out exactly. I'll say a few words about that in a few minutes. But if you do the crystalline electric field and work out what the orbital levels are, you find you end up with this ground state triplet there. Okay, now just going back to these 2 effects I was talking about in the previous slide, we had the splitting between the d orbitals, which is set by this energy scale delta, which is set by the oxygen atoms, for example, that are sitting around there. Okay, so that's one. We've got the crystalline electric field. The second effect is also this Pauli principle that I was talking about before. The fact that you have to partially fill all these orbitals here before you start pairing them up. Okay, so we got Pauli and we've got the crystalline electric field. And so we have basically 2 kind of energy scales, if you like, that are trading off between each other. We've got this ratio of the crystalline electric field over the energy cost of breaking Pauli's principle. Okay, so if I take that ratio and I make it small, then the crystalline electric is bad news, basically, to start breaking Pauli's principle. So that means J here has to win. This is called the weak crystalline electric field. And that means that if I want to start populating all 5 of these characters, I got to partially fill up these 2 blue ones before I come down here. But the other case is that if that crystalline electric field is massive, then it's going to be energetically favorable to start filling up the bottom TG levels before I start filling up the EG levels. So that's what this ratio here is supposed to tell you about. And these are summarized in these kind of funny diagrams here called the Tanabe-Sagano or the Sagano-Tanabe. I haven't quite worked out who should come first. I think in the papers, Tanabe comes first, so I don't, okay, but that's another discussion anyways. But these diagrams here actually characterize the energy levels of the orbital states as a function of this ratio of the competing effects or energy scales of 10dq, which is the crystalline electric field and Pauli's principle. So you're down here, you have to partially fill all 5d orbitals. When you're up here, 10dq is massive, it's okay to start breaking Pauli's principle. This is the case here of cobalt, actually. So you got 7d electrons. So down here, you have to fill up each of the individual 5d orbitals. But up here, when 10dq is massive, it's okay to do that. And that's indicated here by this little transition here where this 2e level comes down and so on. Now, it turns out mostly for 3D transition metal ions, we're actually down here in this weak limit. Okay, so that's the crystalline electric field sorted out. I should just say, and this is just a detail, is that when you make this mapping down to an effective L equals to 1 state for example, cobalt, iron, or vanadium, usually there's a projection factor that's tied to that. And that really just corresponds to the fact that you get the right angular momentum operators for L of 1. It's just you're wrong by a constant isotropic factor. In the case of cobalt, it's -3/2. You can actually solve this in MATLAB pretty easily, but anyways, these are also tabulated. I think you can get them from group theory. But anyway, so let's look at the case of cobalt 2+. So that's 70 electrons. We're way down in the weak crystalline electric field level. We have an effective L = 1, but we need spin-orbit coupling to come into this problem. And so we got L of 1. If I do the Pauli's counting, I get spin of 3/2. And then if I again apply the addition theorem, I find out that instead of having 2 levels like the dimer, there's actually 3 possibilities. There's the case of a total angular momentum of 1/2, 3/2, and then 5/2. And if you do the kind of addition of all the states here, you see, I think you get the right 12 number of states in total here. But anyways, this energy scale here corresponds to a nice clean crystal field transition from J = 5 to this 3/2 state at higher energies. Now, in condensed matter physics, I think in magnetism, this bit of physics I've been telling you about doesn't matter, but it does in a few cases. So let me just explain a case here. This is the case of cobalt vanadium oxides, cobalt 2+, and it turns out this first spin-orbit transition going from that J = effective 1/2 level up to 3/2 here is about 25 to 30 millivolts. So it's about kBT equals to 300 Kelvin. And in this case, this is just kind of academic because the exchange constants are so small that all the magnetic dynamics are happening way down here. So basically, you can treat this like a spin equals to 1/2 system. You don't need any of this multi-level stuff. You can go back to that semi-classical formalism. However, there is actually cases where this isn't true. And this is the case of cobalt oxide. And you can kind of see here why you start running into problems if you start looking at the structure. Cobalt oxide has this, it looks simple, but it kind of falls apart quickly. A simple structure that's the rock salt, where you have a cobalt and surrounded by 8 oxygens. Okay, fine, that's good. So we got a crystalline electric field, fine, that's the biggest energy scale. I've got the spin-orbit coupling, okay, and then I have an exchange talking between the 2 different spins. And so that's J, and I want to figure out what J is. Now, in cobalt vanadium oxide, that case I was showing you in the previous slide, crystalline electric field's the biggest, then you got spin-orbit, and then exchange is way down here. So you don't need to worry about all these higher energy excitations, the 3/2 or these other crystal fields. With cobalt oxide, actually, you have this issue right here, where you got, of course, the crystalline electric field, that's the massive one, it's about an EV, but you have spin-orbit about the same size as this exchange constant between these cobalt atoms. And you can see that, actually, if you think back to what people were talking about in the cuprates, in terms of bond angles between interacting magnetic ions. In that case, what they found was that the exchange constant, as you went closer to 180, actually became massive. And so this is the worst case scenario in cobalt oxide. Just to illustrate that, this is a plot here of those 3 spin-orbit levels. So we got 1/2, 3/2, and 5/2. So I got energy on the x-axis. And then this is the size of the molecular field corresponding to what happens when these magnetic moments start to order and put that molecular field onto an individual cobalt site. So what happens is that's a Zeeman-type field. It corresponds to the exchange constant. And you can see, actually, that for weak J's, it doesn't matter. The J of 5/2 separated from 3/2. So that's fine. But in the case of cobalt oxide, J is so large that you're way up here. And you can hopefully see the issue here, that this is a mess. Actually, you got all the multi-levels from various spin-orbit levels talking to each other. And that semi-classical theory I started off this seminar with isn't going to help you. You need to worry about all these individual levels, and that's why you need the RPA theory behind this. This is just kind of a summary of what cobalt oxide is in the various energy scales. We've talked a little bit about the crystal field. This is just the Coulomb field. Then we have spin-orbit coupling. You can also work in distortions. And then we have this problem of the molecular field. And these are the eigenstates that you come out from solving just the single ion response, not worrying about interactions yet in RPA, is that here's your 3 spin orbit levels. If you start adding a distortion, it doesn't really do much. But the problem is really this molecular field that comes about from this J. So if we want to start looking at excitations between these levels, we need that RPA multi-level theory that I was talking about. And we like to actually call these, we're not the first, this was done back in the 70s by Federer, I think, with crystal field excitations and 4F elements. But the idea of an exciton, why we call them excitons is you've got coupled excitations between spatially diffuse objects. So an orbital degree of freedom, you like to think about it being spatially diffuse. And if you think about an exciton, which is a positron or electron, that's a correlated diffuse object here. So this is our way of actually trying to make the distinction that these are fundamentally different than spin wave excitations. Okay, this is just a summary of some of our calculations. I think you want 5, 10 minutes?
5 minutes.
5 minutes left? Oh, okay. Yeah, we can do that. All right, this is basic, we're getting there. So this is kind of a summary of our excitations compared to the data. Immediately when you do this, you come up with the experimental gap in the excitation spectrum that corresponds to this anisotropy. But interestingly, you also get this diffuse stuff up here, which comes about in the RPA. And these are those amplitude types of excitations. It's just too bad they live up at 90 millivolts, so you can't really control them. After this, we went kind of hunting around for better amplitude mode candidates, and we locked onto this character here. This is calcium ruthenium. I didn't take the data of all. We just wrote down this theory and did the calculation. So this is actually from these people right here. But they attacked this with a very complicated magnetic Hamiltonian with a lot of free parameters. And it's not obvious how you get these guys physically just by looking at the structure. And they were excited in this very weak mode that lives up here, which they attributed to an amplitude mode. So they called it the Higgs mode here. The nice thing, actually, from our perspective, is that if we applied the single ion physics, and this is a little different because you're further down in the periodic table, it turns out the crystalline electric field's a little bigger. And so you're way out here in the Sugano-Tanabe diagram. So you have a nice ground state orbital triplet. You can see, you can model it in terms of the crystal field basis like this, where you pair up one, you got 2 holes here. So we can write down the single ion response, put in an exchange coupling, and actually calculate the neutron response. And actually, we get a very good description to first order of what the excitations are. With a spin-orbit coupling that agrees with other probes, which is always nice, we have a weak distortion. We need to apply the octahedra. But nicely, actually, is that we come up with an antiferromagnetic exchange for the 180 and a minus sign for the ferromagnetic for the 90 degrees, which agrees with good enough Kanamori rules. But we can get all of this just with very simple single ion physics with physical meanings for each parameter. Okay, I just want to finish the talk talking about MgV204. So show you one last example and another kind of interesting bit of new physics that comes out when you start thinking about multi-level excitations, in particular spin-orbit coupling. So I've talked about amplitude modes that come out. Another thing that we went to look at is this compound here. It's MgV204. And the big argument here was what the orbitals looked like. In one case, you had to consider a real basis, and the orbitals had this shape. And in another form, you might think about the orbitals being a complex linear combination of these. And that has consequences for the real space structure. you can see here, these look very different from these. And these have two very different structures tied with them here. Okay, just kind of a quick summary of MGV204. It goes, first of all, through a structural transition, and then a little bit lower in temperature, it goes through a magnetic transition. Just keep that little idea in mind when we talk about the RPA theory here. These are the magnetic excitations. It has your kind of standard spin wave excitation, but a very weak mode up here at 50 millivolts. Okay, so once again, I'm not going to go through this because you've heard this a few times already. We looked at the single ion response, the electrostatic field, spin orbit coupling, and the molecular field, worked out what the single ion Hamiltonian was, and then did the RPA process. Nothing new here. But what we came up with for the fit was this. So we were able to capture this low energy mode with the gap, but also, and unfortunately you can't see it because it's weak, and that's captured in the calculations, is this high energy mode up at 50 millivolts. And that's actually a spin orbit excitation that exists by making a transition from the ground state up to this level here. Now, this is a bit of a spaghetti, but if you follow it back here, you see it corresponds to the spin orbit level, RJ effective equals to 1. The other nice thing about this is we can come up with an energy scale for the anisotropy or the distortion of the local crystalline electric field. Notice that that's much bigger than the spin orbit coupling. And if you think back to what I said just a few moments ago, the system goes through a structural transition first, then a magnetic. And that kind of makes sense because this part in the Hamiltonian just involves the orbitals. So that will distort. The spin orbit doesn't care because it has such much smaller energy scale. And then eventually at lower temperatures, it will go. Now with the case of cobalt oxide, the two are comparable, and you get a structural and a magnetic transition first. Okay, this is basically the last slide. But one thing we actually found with this system, if you start looking at the statics, is because of this multi-level theory and the fact that you get a splitting at low temperatures thanks to the molecular field, notice that if you go down at low temperatures, the ground state is this. But if you start off at high temperatures, kind of the ground state is this. So if you look at diffuse scattering as you cool down, so you're up here at high temperatures, you get this kind of elastic response. I won't say much about this. I just want to point out a difference. And then, okay, you structurally distort, then you get magnetic order. Okay, you structurally distort, and then you get magnetic order. So notice you've changed the ground state. Okay, now when you heat up, so when you come back this way, notice that that's gone. So there seems to be some sort of memory attached with these spin orbit levels when you actually start doing thermodynamics. A nice example of that, and this is the final slide I promise, is this case of sodium cobalt. I don't know how to pronounce this, NBCP, if the chemists can forgive me. Yeah, but anyways, in this case here, if you do the single ion response, you go down to low temperatures, or you magnetically order this thing, for example, by applying a huge magnetic field, you can split that ground state doublet down here. And one of the interesting things that was discovered, I think fairly recently, I heard about this at the APS March meeting, is that if you apply a huge field to this thing at 4 Kelvin or something like, so you polarize all these spins, so you're way down here, and then you slowly decrease the field, so you start turning off this imposed molecular field. Actually, you start bringing these two levels together, and you start getting cooling. And that naturally falls out from looking at this in terms of the spin orbit response. If you start thinking about this as splitting a doublet and you're adiabatically turning off the field, you will get cooling if you want this thing here to stay constant. Okay, I ran a few minutes over, so I'm sorry, JP. But this is the last summary slide. So just to hopefully tell you that we've talked a little bit about spin orbit, what we call excitons. And this is kind of, I think, a progression from beyond semi-classical spin wave theory that I motivated at the beginning of the talk. I think this is important because it gives you new physics. And I showed you the example of amplitude modes that comes about from spin-orbit coupling. I briefly mentioned complex order. And then our recent work thinking about kind of the hysteretic effects that result from this. But hopefully the biggest thing I've left you with is, well, first of all, neutrons are great. But second, that this multi-level single ion physics is actually really important for understanding the ground state properties of transition metal ions in particular. Okay, thanks so much for your time. Appreciate it.
Time for questions.
It's lunch.
Yeah, Spin W. Can you incorporate what you've done into a nice package for everybody?
Oh, can we?
Yeah.
Yeah, okay, we're working on this, actually. So we have a project right now where we could do these, okay, so those, okay, I have to admit, those calculations I showed you, the fit was basically, we have a calculation, we have the data, and we develop a knob until, yeah. So what we'd like to be able to do is a least squares fit. So we're trying to actually develop software package with ICEs based on that. Yeah. So not yet, but we're good. All right.
Also, you show the cerium rhodium indium 5.
Yeah.
And in the paper, you report that 2 magnon continuum.
Oh, yeah. Yeah. Sorry, I can't hear you. No. No, that's actually a really good question. I didn't talk about this. So actually, all the calculations I've shown you, if you think back, okay, I know you don't want to think back to the slide about the Green's function. It's all what's called single particles, so mean field theory. We should be able to calculate this, and we could use a trick from quantum field theory that corresponds to, it's called Wick's theorem. And those continuum, you might have seen it in that slide I showed, those correspond to multi-particle excitation. So those have 2 Green's functions instead of just one. So we haven't done that yet, but that's next up on the, yeah.
So you will be able also, for example, to do, let's say, frustrated system or
Hopefully.
spin liquid.
Yeah, hopefully. I'll say, yeah, I won't make any problems, but yeah, there shouldn't be anything stopping us from that point. I think we tried to set this up computationally once, and it took just too long. But we're almost there. Yeah, okay, thanks.
Yeah.
So I want to make sure I don't take away the wrong message here. Would it be fair to say, based on your talk, that if you have only like 4th row D transition metals,
Yeah.
then you can mostly just ignore spin orbit coupling for most models?
4th row? Yes and no.
It's only really when you bring in the lanthanides that you have to start
Sorry?
the lanthanides.
Yes. Okay, so in lanthanized spin orbit coupling is the biggest, okay, that's the biggest deal. And so then you, spin orbit coupling is really not that important, it's the total J. But you need to start worrying about spin orbit coupling when you're up here. Up at the 4D, particularly the 3D elements. So remember, lambda grows as Z squared. So down here, you're going to inevitably have lambda being a comparable energy scale to the exchange constant. Okay, down here, I know a lot of people think about this being a large energy scale that may or may not be fair. We showed an example of ruthenium where you need to actually understand or put that in to the theory, but definitely you need to worry about it up here and think about how it compares in energy to the exchange constants in your system.
You can come up with like a simple rule for how far apart cobalts should be so that it doesn't interfere, so that you can think about it only from a single ion.
Yes.
Not worrying so much about
Yes.
what is that in angstroms, you think?
Oh, if you want to know the distance?
Yeah.
Oh, gee. Can we put that in terms of J?
Yeah, like for designing materials, like it'd be kind of nice to. Yeah, I mean the J's must be sort of known already for a lot of oxides, for example, right? And so having a rule of thumb sort of for when we can cross over from one regime to the other
I think,
would be useful.
yeah. I think the best, well, okay, right now what I would do is actually calculate the single line response and then get back to you whether the J of a half is talking to the 3 halves level or not. So that distance between the two is about 25 millivolts. So that kind of tells you right there when J, yeah, is important. So I think in cobalt oxide, J was about 10 millivolts. And so that was a big deal. Yeah. Yeah.
Yeah, but I guess there would be no road. It would be complicated.
Yeah, that's interesting.
So student questions? Remember, there's going to be a quiz.
Yeah, does L dot S commute with?
Why are neutrons better than photons?
Oh, that's a very good question, yeah.
Remember?
So you have to answer that before you go to the NCNR tomorrow.
Energy, someone said it.
Yeah. Dynamics, excitations. Any final questions?
Okay, thank you.
Okay, thank you, Chris.
Oh, okay,
Okay, we have lunch, and I want to be back in the room by 1 o'clock prompt, so I'll give you a warning.